Sean Powers is the chair of marine science at the University of Southern Alabama and a senior marine scientist at the Dolphin Island Sea Lab. He has published over 140 peer-reviewed articles and guided over 30 billion in federal and state research projects. His research is at the interface of ecology and fisheries science and includes restoration and conservation of marine resources, including oyster reefs. He serves as the principal investigator for the nearshore injury assessment component of NOAA's Deepwater Horizon Natural Resource Damage Assessment and has published several articles reporting the results of these studies. So we are so glad to have you. When you are ready, take it away.
Thank you. And I've enjoyed the previous two talks, and we hope won't repeat too much of the great stuff that they've talked about, but some of the points I'll emphasize in relation to how we use the science of oyster to assess the injury resulting from the Deepwater Horizon, and then some implications on how we can use the injury assessment results to talk about the restoration planning that's gone into a lot of the restoration. So I'm going to largely talk about impacts that occurred from Louisiana to Alabama, with Louisiana receiving the brunt of the injury to oysters. I'll focus on subtidal oysters and the response of freshwater salinity openings and pumping that water into the system in response to the oil spill. But I'll also talk about some nearshore oysters and some direct oiling. So here you see a conceptual diagram of what we believe was the injury to oysters. And starting at the subtidal oysters, the deeper oysters, and here subtidal means anywhere from 3 to 15 feet. The major impact was from the release of fresh water from the diversion structures in Barataria and Breton Sound. Here the governor's office decided that to combat the onshore flow of oil, that we could combat that to a degree by opening the freshwater diversions. Now, freshwater diversions are open every year. They're generally open in the cooler months when lower salinities would affect oysters the least. But in this case, the oil spill occurred in the summer, and they took the unusual step of opening these freshwater diversions for prolonged times during the summer. When you get to the near shore, and what we mean by near shore is the oysters that fringe the marsh. And here we're talking about less than 5 foot depth within 50 meters of the shoreline. Those were exposed to direct oiling during the oil spill. Oil washed up on the marshes, it coated the oysters, and obviously it had toxicity related to it as well. And that nearshore area also had some response activities, shoreline cleaning, and various activities associated with oil spill response. So all mixed into that is the fact that when we go back to the life cycle that we heard about in the first talk, is that the larvae and eggs are free floating and they would be exposed to the higher PAH concentrations in the water column. So really you have the nearshore oysters affected by direct oiling and response activities, the subtidal oysters largely affected by the response activity of opening the freshwater diversion structures in the summer, and then you have the oyster larvae in the water column being exposed to toxicity. And here's just a summary. We'll talk about nearshore oysters, the direct injury from these, and then subtidal oysters, again, largely a function of the response actions. I should say that nearshore oysters, as we introduce them, are very key to the system and they're really not assessed very well by state agencies because they're difficult to get to. But the more and more we learn about them, the more important they become. Building on Jenny's comments, from a restoration perspective, they're also very expensive to restore compared to subtidal oysters. And in fact, most of the nearshore restoration activities are in fact driven by local groups that can mobilize a lot of labor and a lot of volunteer labor. So we'll focus mainly on the nearshore first. And this is the area where the oil came directly onshore, coated marshes, coated the oysters that occur there. So you have physical smothering of the oysters that cause the decline. You also have toxicity of the PAH components, largely of the oil, that cause declines. And then we'll talk about the connection between oysters and marsh and what the loss of oysters meant to that marsh. So here's a typical picture of what was going on in Louisiana, mainly during the oil spill, where you had oil spill response teams working on the shoreline, trying to mitigate the effects and remove the oil as much as possible. So you can see here, by the time it got onshore, it was more of a goopy substance that could easily coat plants and oysters. Again, there's direct toxicity from the PAH component. And then there's the shoreline response activity. And this is very similar. We'll draw parallels with the Exxon Valdez oil spill and the response activities there and some lessons learned. But kind of keep this in mind when you're thinking about the nearshore oysters. And I've tried to limit the data graphs I'm going to show, but I have to show a few of them because I'm a professor and I'm used to putting people to sleep in my lectures. And you see that at the percent cover of oyster habitat on the left side versus the category of oiling. So some shorelines experience heavy persistent oiling. So that is lots of physical fouling. Oil was present on multiple visits to the site. And you can see the percent cover of oysters is only about 2%. So that's the area outside the marsh. On average, you could find oyster habitat in about 2% of the bottom. And the more lightly oiled areas, that increased to 6%. But that was much lower than where we saw no oil observed, which was 10 to 12%. And that number by itself is very impressive, that thinking that on average in the salinity regime that we looked at, that 10 to 12% of the bottom adjacent to marsh had oysters. So if you extrapolate that to the linear miles of shoreline in Louisiana, that's an incredible resource, and a resource that I mentioned earlier that isn't harvested. It's not harvested for a couple of reasons. One, it's just inaccessible. The second is the oysters aren't as pretty as the ones that are kind of draw the highest price for the raw trade. And the fact that a lot of these areas are closed because of public health concerns, because of the high fecal coliform levels close to the shoreline in many systems. If you look at the next figure, that talks about the treatment. So we're trying to separate here what's a result of the direct oil smothering and toxicity versus the actual shoreline response activity. And you can see the no oil, again, had about 10 to 12% of the bottom covered with oysters. The not treated, so no response action was taken in the area, but we observed oil, was about 8%, and the treated was about 4% cover. So you do see that there's probably a linkage between how intensive the shoreline response activities were, just because of the physical disturbance, and the decline in oysters. So, and we'll talk a little more about this dichotomy almost of the considerations of response actions with oil, and what degree of response actions you want. So, but the take-home message here is that the fringing oyster is abundant normally, and it's definitely impacted by oiling. So how many oysters? One of the things that we were challenged with the damage injury assessment is, because it's a legal process, is you can't just leave it there. You actually have to calculate how many oysters were killed, so hence how many the responsible party has to replace. So the total loss in that nearshore band, and you can see, was about 479 acres of oyster habitat that included about 34 million oysters. And that's total oysters, all size categories. If you translate that to market equivalents, the larger 3-inch oysters plus those that you would have expected to grow up to 3 inches, the number is around 16 million. So that's a tremendous amount of oysters lost. And while the acreage compared to some acreage estimates we've seen doesn't seem that large, 479, Jenny talked about, how much it costs to restore 20 to 60 acres of marsh. And you can imagine, especially for the nearshore environment, the level of community effort and volunteer response that it would take to restore this much oyster habitat. One of the things the data set allowed us to do is look at this issue of the facilitation between two ecosystem engineers, the Spartina marsh in this case, and oysters, and the shoreline protection benefit that Jenny covered so well. And so we were able to look at marsh erosion in areas that experienced decline of oysters and in areas that didn't experience decline in oysters. And again, a couple of graphs. So this is shoreline erosion. This is meters lost per year, per the 2010 to 2013. So meters lost over a 3-year period, where the habitat was absent or severely reduced, I should say, and where it was present. Now, these marsh erosions are staggering. 8 meters lost over 3 years. This is the product of working in Louisiana, where marsh loss is occurring so rapidly. But marsh loss where we had oyster present was reduced to 2 or 3 meters. So we still had marsh erosion, but at a much smaller scale than when the oyster habitat was absent. The figure on the right shows you the EIE scores, or the erosion potential. And we were very concerned that did oil only come up where erosion was intensive because of wave activity and fetch and various things that could complicate our results. But this tells us that the erosion potential was similar between areas with oysters absent and oysters present. So this demonstrates that it's definitely a direct linkage with oyster habitat loss as a result of oil toxicity or the response activities that occurred on the marsh. So this loss, it particularly is alarming in Louisiana, where they don't need anything to accelerate the loss of marshes in the system. And we were able to calculate the acreage of marsh loss because of the loss in oysters, and were able to add that to the injury estimate that the responsible party eventually settled and accepted. So that's kind of the short summary of the nearshore oyster injury, which was very pronounced and obviously disrupted a very important facilitation between oysters and the marsh habitat. Largely, the offshore or subtidal component is associated with the release of freshwater diversion. And we have to take a step back and understand where oysters occur. And this is a figure I like to show that I borrowed from Earl Mawson at Nicholls State, who first introduced this concept that I call the thin green line. And that is that oysters have a large tolerance for salinity, as we've learned in the first talk, anywhere from 0 to above 35 parts per thousand, they can tolerate for some time period. But because of the physiology mixed in with the ecology, mainly the predation and disease mortality, oysters really only occur in a very thin band. And this is normally salinities in the teens. And that's what you see by this wet dry zone that Earl has drawn on this map. And that is the average salinities in the teens, because you generally get higher salinities when oysters recruit to the system, which oysters like to recruit at higher salinities. And then you get periodic freshwater flushings, which we've learned are good for oyster reefs. They bring in nutrients and they also limit predators and disease. So even though oysters can occur over a wide range of salinity, they really only thrive in a narrow band. And so anything that adjusts or moves that narrow band has the potential to cause lots of mortality. And Megan LaPierre's group did an excellent job of summarizing pretty much all the salinity and temperature data and looking at the monitoring results, and essentially have a model that's temperature dependent, as we heard earlier, but it mainly shows you that salinity, the mortality is associated, higher mortality is associated with both lower and higher salinities. And it's those salinities in the teens, the 10 to 20 area, that promote the lowest mortality or highest survivorship. So in Mobile Bay, we've been able to define those areas. And then even on Jenny's maps, you could see the suggestion of a thin green line area where oysters thrive in the system. So what happened during the oil spill was the governor's office decided that oil contamination of the marshes, mainly it was a consideration of the marshes, not so much the oysters, could be mitigated if the freshwater diversion structures that normally operate in the winter could be opened and reduce the salinity in the area and cleanse those marshes with a sheen of fresh water. Now here you see the results of this in Davis, from the Davis Pond diversion, which is in Barataria Bay. And you see in the yellow, the oyster habitat. And then you see here the difference in number of days where it's less than 5 parts per thousand, which is extremely low salinity. And the lighter colors result in the areas that experience prolonged decreases in salinity. So on the magnitude of 60 to 90 days. And this is in the hot summer months where oysters are very susceptible to mortality associated with low salinities. So as we talked about earlier, salinity is a very delicate thing with mortality. And there was a professor who just passed away recently, Sammy Ray at Texas A&M, that would pound his fist on the table and remind everybody that it was salinity that we had to focus on first and foremost. And this is clear in the mortality that we see. When we lower the mortality, when we lower the salinities, we increase the mortality. And you see that same pattern in number of days of less than 10 parts per thousand as well. So if you look at the exposure map, and this is the exposure to low salinity for more than 30 additional total days. So take a normal summer and then impose 30 additional days of low salinity on it. And you see the mortality curve on the right, and the mortality with number of days versus lower salinity. And the more and more you go out and the more exposure they get, the more mortality that would result. And that's actually based on trays that Louisiana Department of Wildlife and Fisheries has put out and we used during the oil spill. So now here is the calculated injury. And if we look at, these are various ways of using the data, but what I want you to focus on is the Nestor tray NERTA bottom line number. And you see 3.5, and that's 10 to the 6, so 3.5 billion oysters, market and seed size, were killed during the spill. If we express that as market equivalent, those oysters that would be expected to grow up to 3 inches, that number is still extremely high, just under 3 billion. So that is a tremendous amount of spawning potential as well as direct injury that resulted from a response action due to the spill. So a lot of people have asked, was there rationale for the response activity? And like I said, the primary motivation was thinking about marsh and marsh vegetation, but we've done some experiments where we looked at the effect of short-term low salinity on oysters. And short-term here we mean by 21 days. And we had several treatments where we look at low salinity, medium salinity. Low salinity is 8 to 10 parts per thousand. Mesohaline or higher salinities are 15 to 18 parts per thousand. And different combinations of oil and dispersant on juvenile oysters. And what we found is, again, if you look at the graph on the left, in the control during the low salinity, we had high survivorship at either salinity, the low or the mesohaline. If we had dispersed oil or oil, the effect of low salinity tended to reduce the mortality effect. So we had higher survivorship. And the reason that happened is we think that physiologically the oysters shut down during these low salinity events, and so they're not taking up as much of the toxic elements of the oil compounds. So over short time periods, the rationale actually bore out in the experiment. Obviously, we didn't manipulate the high temperatures and the 60 to 90 days where we would expect all mortality. And you can see here that dispersant increases the mortality of oysters. And that's largely what we see for other taxa as well, other groups of animals. So finally, one of the issues we've looked at is the importance of, for restoration of the connectivity between nearshore and offshore oysters. And we did this with a modeling environment called ADCIRC, which is an advanced circulation model. And interestingly, for oysters that have oyster larvae that have a subtidal origin, most of those settle in the subtidal and not too much in the nearshore. For oysters that are in that nearshore environment, they not only feed the nearshore system, but they feed the subtidal system. So it makes those fringing marsh reefs even more important. And like I said, the problem with that is those fringing marsh reefs are the most expensive to restore, order of 10 to 12 times as much per acre. So wrapping up, we see that oiling and response actions to the oil spill killed oysters on the millions to billions scale during 2010. The injury resulted in substantial reductions in fisheries yields as well as ecosystem services. Many sites that had productive oyster habitat continue to show loss, and that's as of 2017. Many of the sites just didn't recover. They just didn't rebound. And we see the reasons why in the earlier talks. You could have erosion of the shell system. You could have a variety of lower recruitment because of the reduced spawning stock. And oyster shells, as we're learning, only have a certain life. And maybe the recovery took so long that those oyster habitats simply aren't there anymore. So in talking about oil spills, very similar to the lessons learned from the Exxon Valdez oil spill, which I'm not old enough to have worked on, but actually did some synthesis work on. The pros and cons of response actions need to be thought out prior to the next oil spill. And that is this issue of freshwater releases and how effective it was for oysters as well as the marsh. Shoreline response actions, and do we need to clean up every shoreline and try to remove all of the oil? The use of dispersants is a significant one. Obviously, in the nearshore environment, dispersants were not used in our deep water oil spill, and dispersants were only used on a very limited scale for the Exxon Valdez oil spill as well. And then the issue of fisheries closures and how long those fisheries closures need to persist. And in particular, a lot of areas opened up their oyster harvest to intensive harvesting before the oil came on shore. And how did that affect our results, and how did that affect? And finally, restoration activities need to focus on both nearshore and the subtidal oyster beds. So I know I've covered a lot of things with the injury assessment. There's a lot of papers now that come out documenting what we've done, and I've put them here. But hopefully I've given you an overview of at least what the process is and how we use the science in assessing the injury.